Sorry, here. Yeah, let's do this. So before we get going with notes here, I sent an announcement real quick, but I imagine not all of you saw it. So let's watch this little video about what a radian is, because I think it does a pretty good job of making it clear what we're talking about. So everybody ready? Here we go. It's short. Just turn the volume.
This video illustrates the definition of a radian. First, begin with a unit circle. Now, consider an arc length equivalent to 1 radius. The measure of the angle subtending an arc length of 1 radius is 1 radian.
I'm gonna stop right. Oh, you can't see the picture when it stopped. That's annoying. But you can kind of see it. If I do that, if I do that, if I do that. I was there. Cool. So I just want to make that super clear. That's kind of the whole deal, is that when we're talking about an angle measure of 1 radian, that angle there is 1 radian. It's approximately 57 degrees. That angle being 1 radian just means that this arc length here is exactly 1 radius long. So that's what a 1 radian is. It's an angle, and it's the angle that is that I always mess up the words here. It's the angle subtended by an arc length that is 1 radius worth long. Okay. We'll continue. The rest of it's not as exciting. It's a little while.
If we double the arc length, so that now we are viewing an arc length of 2 radii, then the new angle, 2 radians.
Seems reasonable.
The connection between arc length and subtended angle. The formula for arc length is L equal radius times angle in radians. Put another way, the angle in radians is the subtended arc length L divided by the radius.
I'm going to pause it there because I feel like he said enough. I like this little video because I think it really makes the picture clear. My picture is not going to be as nice, but I think that's enough of that. So the rest of it's just talking about kind of the rest of what you get. It looks super dark. Can I brighten this up a little bit? So we're going to talk about radians. I'm going to grab this paper, but that's kind of the big deal, is that when you're talking about a circle, and it doesn't matter how big the radius of the circle is, any circle, which we'll see how well I draw this here. That's pretty good. This pen is trash. So no matter what the radius of your circle is, if you take that length and look at the arc length over here, if that arc length is the same as your radius, then this angle is equal to 1 radian. And the way they're getting that angle is literally by taking this length, this arc length here, and dividing it by the radius there. So that angle theta is equal to the radius divided by the radius, which is 1 radian. This might feel kind of, I don't know, a little hand wavy. So let's look at some real numbers for just a second. Let's pretend I drew a good circle. You all can pretend that for a minute. And let's say that the radius of the circle was actually, I don't know, it looked like about 3 centimeters. Approximately. And so then if I go again, my circle, not excellent here. If I go 3 centimeters along the circle, that angle, sorry, 3 centimeters along the arc, that angle there, theta is exactly equal to that 3 centimeter length, which we typically call S, divided by the radius, which we typically call R, which is just 1, in this case, radian. It's also kind of interesting, this is not super important, but it's kind of interesting that the units cancel, like the centimeters and centimeters cancel out. So radians are actually called a measure without dimension. There is no centimeters, there's no degrees or whatever. Radians are just kind of this thing that don't have any, but not the super important one here. And so then if we go another, I don't know, let's say we went this far, let's say we did a whole another 3 centimeters, so that the arc length here for this new angle, let's call it beta, this arc length is 6 centimeters. Wow, my drawings are excellent today. Okay. So here we have a 6 centimeter arc length, and the angle beta, I'm calling this larger angle here, beta is just equal to 6 centimeters divided by 3 centimeters, or your arc length divided by your radius, which is just 2. And usually we just write 2. So if someone says, what's the angle? And someone says the angle is 2, they mean 2 radians. On the other hand, if they mean degrees, they have to say degrees. So before we get too much further into this, I just want to ask anybody, are there any questions so far? We're about to make it nicer, but I just want to ask if there are any questions about what we've said. I'll point out one more time that 1 radian is close to 57 degrees. I don't remember the decimal. That angle there, that looks like it's about 57 degrees, right? We have a much more intuitive sense of how degrees look. Okay, so again, I know there's some extra paper in your, like, if you look at there's an extra page at the back if you want to use that. Right? Sorry, I should have said that before. I know you don't have to write all this down. It's always the case. But what I want to point out is, all right, let's draw a better circle, James. That's okay. So here's where we get the relationship between radians and degrees. A circle, a full circle, has how many degrees? Right, full circle, 360 degrees. And the question is, if the radius is just R, gosh, all my pens. I need to buy some new pens, I'm determined. The radius is just R. What's the arc length all the way around the circle? Or in other words, what's the circumference of the circle? Well, the circumference of a circle is 2 pi times whatever the radius is. The radius is 1 inch, the circumference would be 2 pi inches, which again, not a lovely number, but it is what it is. So if we go all the way around the circle, keep going all the way around, that length is exactly 2 pi times whatever your radius is. And so if we call that arc length S, and we want to find out what the amount of radians is, which is the angle theta, which is 360 degrees, is also the circumference or the arc length divided by the radius. The radius is the radii cancel, and we get that 1 full revolution, the angle for 1 full revolution is 360 degrees or 2 pi radians. Because again, you're just saying there's 1 radian. Here's my picture's probably going to fall apart, but I'll try to do the best I can. There's 2 radians. There's 3 radians. There's 4. There's 5. There's 6. And my picture is not the best, and there's a little bit more, but it looks like a lot more. So 2 pi radians, approximately 6.28 radians. So 1 full revolution, 2 pi radians. And the relationship we usually go with is that half a revolution that angle, 180 degrees, is just half of 2 pi radians, which is pi radians. But it really, really wants you to have a sense of what a radian is, right? We're just saying, oh, the radian is the angle you get if you go 1 radius length along the circle. Pi radians is the angle you get, right? That's pi radians when you go pi radius lengths along the circle. That is pi times the radius, whatever that radius length is. Okay. So that's the understanding part. The rest of what we do with this is very kind of mechanical, meaning we're going to take this relationship that 180 degrees is equal to pi radians and use that to help us convert from degrees to radians or from radians to degrees. And this is kind of what we use almost all the time. So, get my notes here, sorry. To the actual notes at hand. We try to not write all over them, like I sometimes do. Again, if there's questions, you're welcome to ask them. So, given or knowing that we have pi, and again, people aren't going to write radians usually. You can write pi radians, rad for short, is equal to 180 degrees. And if we divide both sides by either thing, you can say pi radians divided by 180 degrees is equal to 1, or 1 is equal to 180 degrees divided by pi radians. It's like a conversion. It's like converting from feet to inches. You multiply by 12 inches per 1 foot because you're really just multiplying by 1. The same idea here. To convert from degrees to radians, we're going to multiply by, you always multiply by the thing that you want to end up with on top. So if I want to end up with radians, I'm going to multiply by pi radians over 180 degrees. And to convert from radians to degrees, we're going to multiply by 180 degrees over pi radians. You could also use 360 over 2 pi or 2 pi over 360, but usually it's easier to do pi over 180. Why do we care about this? For a couple reasons. One, typically when we start graphing trigonometric functions, it works better to be in radians than it does to be in degrees. Two, degrees are kind of an arbitrary made up amount. Whoops. Sorry. So, right, there are good reasons for picking to have 360 degrees in a circle, but somebody just picked that, right? There wasn't like, someone's like, oh, well, this is a degree, right? We all decided this certain length of an angle is a degree. Someone just said, well, there's 365 days in a year. 360 seems like a good number. It's divisible by a lot of things, right? 360 can be divided by a lot of different numbers equally. And that was two of the reasons why that number was picked for the number of degrees in a circle, but it's arbitrary. You could pick 100 degrees to be in the circle or whatever amount you want. In fact, there is a way people have picked like this. I forget what it's called. I think they're called like gradients, I think. Like there's like, if you divide a circle into 100 equal pieces, angles, that's another way of measuring angles. So it's an arbitrary thing, whereas radians are not arbitrary. There's only one way of saying this is 1 radian length, because that's whatever the length of the radius of the circle is. So radians are purely not arbitrary. You're stuck with them the way they are and they can't be changed. Which is kind of great because we don't like things to be arbitrary if we can help it. Okay, so that said, the converting is not too terrible. If I want to convert from 30 degrees to radians, I'm going to take my 30 degrees and multiply it by pi divided by 180 degrees. The degrees will cancel. So then I usually like to write this as 30 pi over 180 and then start reducing. You can certainly divide top and bottom by 10 and reduce that to just 3 pi over 18. And then 3 and 18 both have factors of 3, so I can reduce that further to just pi over 6. When converting either way, we should reduce as much as possible. Similarly, if I want to convert 120 degrees to radians, I'm going to multiply 120 degrees by pi over 180 degrees. again, the degrees cancel. I get 120 pi over 180. I could probably skip that step and go straight to 12 pi over 18. And then I can either divide by 3 or divide by 6, whatever is more convenient, and end up with 2 pi over 3. Why don't you all try converting 40 degrees to radians? So should be similar. 40 times pi over 180. Degrees cancel. I'm going to cancel the zeros as well. I'm going to get 4 pi over 18, right? Instead of writing 40 pi over 180. It's a pretty easy cancellation to do. And then I can reduce that to 2 pi over 9. And that's as far as I can go. We definitely don't want decimal approximations here, right? We don't want to plug this into a calculator and say, I don't know, 2 pi over 9 is going to be approximately like 0.67-ish radians, I would guess. That's not the answer we're looking for. We want an actual nice expression here. We don't need to, but you could, if you wanted to, write radians, radians, radians. But if someone asks you for an angle, or if someone gives you an angle and they haven't said degrees, you should assume they mean radians, unless they say, well, I would say if they, yeah, I don't know. That's a tough one, because if someone said like 30, you're probably thinking degrees, not 30 radians. But in this class, I will be very specific. I will say degrees when I mean degrees, and I will not say degrees when I mean radians. But I probably won't say radians. I'll just say the thing. We can go the other direction as well. We can convert from radians to degrees. These are both radians. So pi over 10, I'm going to multiply that by 10, not an 18. Got ahead of myself. By 180 degrees over pi. And if you're given a nice-ish angle that has a pi in it, because it's in radians, then the pi's will end up canceling. And we'll get 180 degrees over 10, which is going to reduce to just 18 degrees. And it is measured in degrees. So the degrees don't cancel like they did in the previous ones. This is a negative angle. And what I'll say about that for now is that when we're measuring angles, we typically measure them in standard position from the positive x-axis. So like the origin is kind of the center of the circle, and you're measuring angles from the positive x-axis. And if it's a positive angle, we go counterclockwise. If it's a negative angle, we go clockwise. So that's the difference. Positive angles, we go clockwise. Negative angles, we go counterclockwise. We'll talk more about that later, but since there is a negative angle there, I felt like I should say something. The result still ends up being the same. We still multiply by the same conversion factor, 180 degrees over pi. The pi's cancel nicely, and left with -3 times 180 divided by 5. And typically, when I have something like this, I usually find it easier to do the division first instead of the multiplication. It might not always be true, but generally, if I'm doing this, it's usually easier to divide first. 180 divided by 5. Never good at dividing by 5, but I'm really good at dividing by 10 and multiplying by 2, which achieves the same result. So I divide by 10, I get 18. If I multiply by 2, I get 36. And that is what 180 divided by 5 is. So I can think of this as -3 times 36 degrees, which might not really feel easier, but it's the way my brain went. 3 times 36, well, 3 times 30 is 90, and 3 times 6 is 18, and 90 plus 18 is 108. So that's what I'm thinking of when I do this. It's also perfectly okay to use a calculator to simplify these things, but just be aware of what you're doing. Try to make it easier on yourself. We probably also could have done the multiplication first, like 3 times 180 is 540, and then divided by 5, but that seems less easy to me. So I would try to take the route that's simpler calculation, but however you want to get there is okay. So converting between degrees and radians is a pretty straightforward process. Sometimes the numbers get a little bit gross. For example, if you were trying to convert something like, I don't know, 7 pi over 4 radians, it's going to be a little bit gnarly. When you multiply this by 180 over pi, the pi's cancel, and then you've got 7 times 180 divided by 4. So 180 divided by 4 does work, but 7 times, so 180 divided by 4 is 180 divided by 2 twice. 180 divided by 2 is 90, 90 divided by 2 is 45. The 7 times 45 is not my favorite, but we could do that. Or you could say, I'm going to make this 7 times 90 over 2. I do one of those divisions. And then 7 times 9 is 36, sorry, 63. So 7 times 90 is 630. So then you've got 630 degrees over 2. And that feels easier to me. That's going to be 315 degrees. Again, you can do whatever tricks you want. You can make this work however it works for you. I'm just trying to show you my way of thinking about this. Okay. So trigonometry is, I don't want to say mostly about, but is a lot about the trigonometric functions. Sine, cosine, tangent, secant, cosecant, and cotangent. And when we write these things, we typically, although not always, but we often think about them in terms of right triangles. So these are both right triangles. They've got right angles right here. And if we pick one of the other two acute angles, meaning angle less than 90 degrees, I'm going to call this angle theta or this angle theta. Where you think of the angle you're looking at being determines what we call the rest of the sides of the triangle. So in a right triangle, and only in a right triangle, the side opposite the 90-degree angle, or the longest side, same thing, is called the hypotenuse. So this is the hypotenuse. Wow, I can spell. Hypotenuse. This is the hypotenuse here. We're going to label that with an H. Now, in this triangle, since I picked this angle to be theta, I'm going to call this side over here the opposite side. So this is the opposite. Same deal here. Since this is the angle theta, this side that's opposite of it is what we're going to call the opposite. The opposite side should always be the side that essentially theta isn't touching either one of the sides. Theta is between two of the sides, and the side that's not between is the opposite side. Same here, same here. And then finally, the side that's next to the angle that isn't the hypotenuse is the adjacent. So after we label the sides of the triangle correctly, then we define the trig functions in the following way. So sine of theta is defined to be the opposite side divided by the hypotenuse side. I should say the opposite length divided by the hypotenuse length. The cosine of theta is defined to be the adjacent length divided by the hypotenuse length. And the tangent of theta is defined to be the opposite length divided by the adjacent length. And then the other three trig functions, cosecant, secant, and cotangent, are the reciprocal trig functions. And they are written in this specific order so that their reciprocal nature is really shown. So the reciprocal of sine is cosecant. Reciprocal. Cosecant is 1 over sine, or the reciprocal of opposite over hypotenuse is hypotenuse over opposite. And the reciprocal of cosine is secant of theta, which is 1 over cosine of theta, which is, if cosine is the adjacent over hypotenuse, secant is the hypotenuse over the adjacent. And same thing for tangent and cotangent. Tangent is the opposite over the adjacent. Cotangent is the reciprocal, the adjacent over the opposite. Also 1 over tangent. I think there's something else I want to say here. No, that's fine. So these are definitions you definitely want to be aware of. This is when I'm thinking about sine, cosine, and tangent. This is one of the first things I think of, but not the only thing. There are definitely other ways of imagining these as well. There is definitely a mnemonic device many people have learned over the years. I will tell it to you now if you haven't heard it before, or even if you have. It is people. I've seen people write this in cooler ways than I'm about to, but I'm going to write it as so ka toa. Make sure you emphasize the ka part. I've heard people say cosine is opposite over hypotenuse because they said so toa, and they've kind of said that more as an O sound than an A sound. But it is so, sine is opposite over hypotenuse. Ka, cosine is adjacent over hypotenuse. Toa, tangent is opposite over adjacent. There is not, at least to my mind, a similar nice thing for the reciprocal ones. Like I've tried, people have tried, like it's like cha sha ko. No, it doesn't. It's not good. It doesn't work. Oh, I know what it is. I see people write like this. They've written it as so ka toa. To emphasize the fractional relationship nature here. I'm going to say something. It's not a big deal, but it kind of is. Trig functions are just ratios. It's just one length divided by another length. And someone once upon a time decided these are what we're going to call them. Sine is just this side divided by this side. Cosine is just this other side divided by this other side. Tangent is just this other side divided by this other side. And there's only 6 of them. Because if you've got 3 sides of a triangle, there's only 6 different ways you can divide one side by another side. It's true, right? You can either do this one divided by that one, or this one divided by that one, or that one, or this one divided by that one, or that one. That's 6 different ways of doing the division. That's why we've got 6 different trig functions. I'll find out later. I'll share. There's a funny comic about this that maybe you'll all appreciate. Maybe not. Maybe you'll think it's dumb. I thought it was funny. The next thing I'll say is, I really, really strongly encourage all of you to say the trig functions the way I'm saying them. Say sine, say cosine, say tangent. Say cosecant, secant, and cotangent. I'm not even going to say the other things that you might have said because I think they sound terrible and I don't want to say them or encourage them. If you say them differently, it's totally fine, but people will understand what you mean more if you say sine, cosine, tangent, secant, cosecant, secant, and cotangent. Yeah. So we can use these trig functions to find the trig functions of any given right triangle. So here's a right triangle. It is right. Although if it's going to be a right triangle, they should typically draw that little square thing in the corner to really make you know that it's a right triangle. If they don't, you can be like, well, maybe they just did a poor job drawing. So in this triangle, for that angle theta, 4 is the opposite side, 3 is the adjacent side, and we don't actually have the hypotenuse. We have to find it. So typically, or often in the right triangle, we will not be given one of the 3 sides, and we have to find it using the Pythagorean theorem. So just to make sure everyone's on board, if you've got a triangle, it's a right triangle, and it's got some sides A, B, and C, the Pythagorean theorem says that A squared plus B squared is equal to C squared. And I would point out that it's always the 2 smaller sides squared added together equal to the larger side squared. Or essentially, the hypotenuse should always be the one that's by itself. Hypotenuse is the lonely one. So in this triangle here, we're going to find the third side before we start finding the trig function. So let's call it C, or whatever you want to call it. And then we're going to say, okay, 3 squared plus 4 squared equals C squared. And we're not going to get C equal to 7, right? We can't just take the square root of everything and say 3 plus 4 equals C. We have to actually do the math and add them together before we take the square root. Let's see, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. 25 equals C squared, and C is going to equal, even though if we were solving this, we could say plus or minus the square root of 25. Since we know it's a length, it should be a positive number. So we're just going to say it's positive square root of 25, or just positive 5. So C is equal to 5. So our hypotenuse has a length of 5. This is probably the most famous right triangle, the 3, 4, 5 triangle. You'll notice that in this triangle, it's not drawn very well, right? The longer side is the side that's labeled as 3, and the shorter side is the side that's labeled as 4. You should just ignore that. So if someone draws their triangle badly, they still expect you to use the triangle they've given you. So try not to pay too much. Like I did this on, like, it wasn't just an accident, actually, it was on purpose, right? Sometimes people are just going to draw triangles that look wonky and label them in the way they want them to be. A lot of math sometimes works that way. Like, here's my picture. It's good enough. I'm going to label it the way I want it to be, and you're going to deal with it. So don't look at the lengths to be like, yeah, I know this one looks longer, but I'm calling it the shorter side. Oh well. So sine of this angle, well, sine is the opposite side divided by the hypotenuse side, so it's going to be 4/5. Cosine of theta is the adjacent side divided by the hypotenuse side, so it's going to be 3/5. And tangent of theta is the opposite side divided by the adjacent side, which is going to be 4/3. If you're finding all 6 trig functions, I do recommend writing them in this specific order. Sine, then cosine, then tangent, and then to the right, cosecant, then secant, then cotangent. And the reason is because once you have these first 3, the other 3 reciprocals, you're just literally taking the reciprocals. So cosecant of theta, I gotta be honest with you, I'm never thinking of cosecant of theta as hypotenuse over opposite. It's just not something that's stuck inside my brain. What I'm thinking of is, oh, cosecant's the reciprocal of sine. Sine was 4/5, so cosecant's going to be 5/4. That's really what almost any, well, I don't know. I'm not in anyone else's head, but I imagine that's how most people are actually doing it. They're not thinking of cosecant as hypotenuse over opposite ever. They're thinking of it as the reciprocal of sine. And sine is 4/5, so cosecant's 5/4. Similarly, secant is the reciprocal of cosine. So if cosine of theta is 3/5, secant of theta is 5/3. Cotangent is the reciprocal of tangent. Tangent of theta is 4/3. Cotangent of theta is 3/4. That's what I would recommend if you ever have to find trig functions of angles. If you're finding cosecant or secant or cotangent, you want to find their original sine, cosine, or tangent first, and then find the reciprocal of that to actually find it. Also, that's how most calculators are going to work too. Most calculators don't have a cosecant, secant, or cotangent button. They have sine, cosine, and tangent. You can use those, and then you can take the reciprocal of whatever you get to actually find secant, cosecant, and cotangent. Oh yeah. Sure. So sometimes you will need to use a calculator to evaluate a trig function because we just don't have the tools for it. So, and that's something that is on this homework assignment. So look out for that. Be careful. If there's a degree symbol, you need to make sure your calculator is in degrees mode. So sine of 2 degrees, if you calculate that, it should come out to be approximately 0.0349. I would encourage all of you to do this at some point to make sure you can tell the difference between your calculator being in degrees or radians. This cosine of pi/5, that's an angle that's measured in radians. And if you put that into a calculator, you're going to get approximately 0.809. I should point out, these are both approximations. They're not exact values. Most of the time with trig functions, you're not going to get exact values. You're going to get approximations. I will also point out, if you were trying to find, say, like cosecant of 45 degrees, well, if you don't have that button on your calculator, which I can't imagine any of us do, what you're going to do first is you're going to find sine of 45 degrees, which is approximately 0.707, I think. Let me double check. Pretty sure about that. I didn't have it written down. That's why I'm fairly certain. Let's find out. In fact, let's talk. So, sure. So there's my terrible phone calculator. And I know that I'm in degrees because that little button there says you could switch to radians. So if you want to change from degrees to radians, you click on that. Now you're in radians. You can click on it back to be in degrees. So whichever one you don't see on the phone calculator is the one you're in, which is kind of annoying, but such is life. So I want to find sine of 45 degrees. Yep, 0.707 approximately. And then if I want to find cosecant of 45 degrees, I would take the reciprocal of that. So there's my reciprocal button, 1/x. So there's my cosecant of 45 degrees, approximately, well, exactly 1/sine of 45 degrees, which is approximately 1.41. So that's how you deal with the reciprocal trig functions if you're using a calculator. And from a time before, calculators, yeah, whatever. Sometimes calculators are allowed, depends on your class. We're not going to worry too much about it. So here's what we really want to get from these angles and trig functions. There are some angles, 3 of them specifically. Well, okay, 5 of them really. But there's 3 angles we're talking about right now that people are going to ask you to find sine, cosine, tangent, secant, cosecant, cotangent of all the time. Like they're just going to come up and people are going to be like, you should, they're going to expect you to know how to find cosine of 30 degrees off the top of your head without going to some other source. And so it's going to come up relatively frequently if you're dealing with trig. More likely to come up in the 17 and the 21 series, less likely in the 16 series, but still does come up in the 16 series. So you will see trig in all of them, just less so in some of the others. Okay, so there's a couple triangles here. And typically, when I think about this first triangle, I really think of it as, can I trace? I can trace. Yeah, I like tracing. I'm really thinking of it as half of a square. A square of length, side length 1. Don't worry, you don't need the square. I'm just showing you where this comes from. So in this square, all of my angles are right angles. And if I cut the square in half, what are these 2 angles here that were 90 degrees before I cut them in half? 45 degrees. Or in radians, pi over 4 radians. So 45 degrees times pi over 180 is 45 pi over 180. And really, I think it's worthwhile to see that, oh, 180 is 45 times 2 times 2. But you can also do the dividing, right? I can say, well, they're both divisible by 9. So 45 divided by 9 is 5. 180 divided by 9 is 20. And then 5 over 20 reduces to 1 over 4, or pi over 4. So 45 degrees is pi over 4. That relationship comes up a lot. I would encourage you to get comfortable with it. So here we have this right triangle with the angle being, you can call it 45 degrees. We call it pi over 4. Same angle. It's the only right angle triangle that is isosceles, meaning both of these sides are the same length. Any other right triangle has different angles, has different side lengths, but this is the one that's isosceles. And if we still call these sides 1 and 1, let's find that third side. It's not going to be a nice integer number. It's going to have a square root. In fact, let's see here. If I say 1 squared plus 1 squared equals c squared, 1 squared is 1 plus 1 squared is 1. 1 plus 1 is 2. So if 2 is equal to c squared, then c is going to be just the square root of 2. So this special triangle, it's in my brain, right? Like I know there's a 45, 45, 90 triangle. Not, in fact, that's what this is called. This is called the 45, 45, 90 triangle. It's never caught on to call it the pi over 4, pi over 4, pi over 2 triangle. It's just not as easy to say. Although that would be fine, right? Those are the angles, right? That angle there is also pi over 4. That angle there is also 45 degrees. That angle there is 90 degrees, which is pi over 2 radians. But we can use this special triangle to find sine, cosine, and tangent of pi over 4 radians. So looking at this triangle, and again, we can use either angle, but let's use this one specifically. So sine of pi over 4 is the opposite over the hypotenuse, which is 1 divided by the square root of 2. Cosine of pi over 4 is the adjacent over the hypotenuse, which is also 1 divided by the square root of 2. By the way, that is kind of the most poignant fact about 45 degrees that I think of. Cosine and sine have the same value for a 45-degree angle for pi over 4 radians. And it's not true for any other acute angle. It's also, if you think about it, 45 degrees is like the line, it's like the line y equals x. I know that's kind of making a leap, But like if you think about the 45-degree angle and the line y equals x, the line y equals x does make a 45-degree angle to the x-axis. And that's kind of a good reason to think about why sine and cosine might be the same. And finally, tangent of 45 degrees or pi over 4 radians is opposite over adjacent, which is 1 over 1, which is 1. Okay, one thing about this is typically we don't like to leave these unrationalized, or we like to rationalize them. So we usually multiply 1 over root 2 by root 2 over root 2 and get the square root of 2 over 2. It's worthwhile to think of it both ways, to be perfectly honest. It's good to know that sine of 45 degrees or sine of pi over 4 radians is 1 over root 2. It's also good to know that sine of pi over 4 radians or 45 degrees is root 2 over 2. They are both good ways of thinking of it. You will see them both show up. And tangent is just one. We didn't write the reciprocal ones because the idea is to find them relatively easily. But if we wanted to talk about them for a second, we could say, oh yeah, cosecant of pi over 4 is going to be the reciprocal of sine of pi over 4. Now let me ask you all, which one is it going to be easier to take the reciprocal of? 1 over root 2 or root 2 over 2? Which one's easier to flip and get a nice answer that we don't have to simplify further? So 1 over root 2, because if you flip that, it's just root 2 over 1, which is just root 2. So cosecant of pi over 4 is root 2 over 1, which is root 2. By the way, the square root of 2 is approximately 1.414, which is what we just did earlier. But you should definitely not, so although I know I just said that, you want to leave your answer as root 2. We do not want a decimal approximation unless specifically asked for. In the same sort of way, secant of pi over 4 is the reciprocal of 1 over root 2, which is root 2. And cotangent of pi over 4 is the reciprocal of 1, which is 1. But the idea most of the time is people ask you just for the 3 primary trig functions, sine, cosine, and tangent, with the kind of idea being that if we can find those 3, finding the reciprocals is a straightforward process. And so we often don't ask about it. All right. And then we have this other triangle, which again, let me point out where I think about where it's coming from. You can do more tracing. Fine. So this triangle is really coming from this bigger triangle, which is meant, although my drawing is kind of crashed, it's meant to be an equilateral triangle. So this equilateral triangle, kind of do that bottom part too big. In equilateral triangle, all the sides are the same length. That's what equilateral means. I'm gonna call them all 2. And all the angles are the same. They're all going to be 60 degrees. Or 60 degrees times pi over 180 is 60 pi over 180, which is 6 pi over 18, which is pi over 3. And then if we cut that in half, well, this angle is a right angle. That angle was 60, now it's 30 degrees. And this angle is still 60 degrees. So that's the idea. That's where this triangle is coming from, by taking this equilateral triangle and cutting it in half down the middle and getting a side length of 2 here. Sorry, 2 here. This side got cut in half. It was 2. Now this half of that 2 is just 1. And we'll figure out the side in a minute. This angle is 30 degrees, or pi over 6 radians. This angle was 60 degrees, or pi over 3 radians. And this angle is 90 degrees, or pi over 2 radians. So there's our other special triangle, often referred to as the 30, 60, 90 right triangle. We got to find that third side. All right, let's call it A for a moment. So be careful when you're using the Pythagorean theorem. The side that is the longest, the hypotenuse, is always the one that should be by itself. So even though the side that we're solving for isn't the longest, we need to make sure that it goes where it's supposed to go. Meaning, when we're trying to solve this, we should be writing 1 squared plus a squared is equal to 2 squared. Or 1 plus a squared equals 4. a squared equals 3, a equals the square root of 3. So that's the third side of our triangle. Something I've noticed over the years with the triangle, with all triangles actually, is in any triangle, the longest side is always opposite the biggest angle. The shortest side is always opposite the smallest angle, and the medium side is always opposite the medium angle. It's always true for triangles. It's kind of neat. So if you're ever drawing this, you're not sure which side goes where, just remember that 2 is bigger than the square root of 3, which is about 1.7, and the square root of 3 is bigger than 1. So that's your small, medium, and big length, and this is your small, medium, and big angle. So we can kind of figure out how to draw it if you've forgotten that. It is a good triangle to know about. And now we can use this triangle to find sine, cosine, and tangent of these other two special angles of pi over 3 radians or 60 degrees and of pi over 6 radians or 30 degrees. So looking at my triangle, sine of pi over 3 radians, I'm looking at that angle. I'm going to go opposite over hypotenuse. So sine of pi over 3 is going to be the square root of 3 divided by 2. Cosine of pi over 3 radians is going to be adjacent over hypotenuse, which is going to be 1 over 2. So nice. Simple fraction. And tangent to pi over 3 radians, again, looking at that angle, I'm going opposite over adjacent. That's going to be root 3 divided by 1, which is just the square root of 3. On the other hand, if I look at pi over 6 radians or 30 degrees, I'm going to get the same value showing up, but for different trig functions. So it's kind of interesting, I think, that if you look at this angle, sine is the opposite of hypotenuse, which is root 3 over 2. If you look at this angle, cosine is the adjacent over hypotenuse, which is the same thing, root 3 over 2. And that's not by coincidence, right? If you have the two complementary angles of a right triangle, their sines and cosines kind of interchange because you're just looking, right? This angle, the opposite side is that side. This angle, the adjacent side is that same side. So you get kind of the same thing. So here, cosine of pi over 6, skipping ahead, cosine of this is adjacent over hypotenuse, which is root 3 over 2. And sine of pi over 6 radians is going to be opposite over hypotenuse, which is 1 over 2. So these kind of switch, not surprisingly. And finally, tangent to pi over 6 is going to be the opposite over the adjacent, which is 1 over root 3. And again, we see something we want to rationalize, so we multiply it by root 3 over root 3 to get root 3 over 3. We will be talking more about these specific angles, pi over 4, pi over 3, and pi over 6, as class goes on. But these are definitely angles that by the end of this class, I would really like you all to be able to memorize, for lack of a better way of saying it. Then there are tricks to doing it. Some people like memorizing in circles. Some people, there's like a finger trick on one of your two hands. You can like put down some fingers and know which one's which. I've never been good at that trick personally, but you can Google it. It's a good trick for some people. But really, you want to be someone be able to ask you, hey, what's sine of pi over 6? And you're like, oh yeah, I know it's 1/2. Like those are the things, these three angles specifically are the ones you want to be able to know how to find sine, cosine, and tangent of without too much thought or effort, because they come up so frequently. All right, I feel like there's still more things to say here. Oh yeah, those are just things. I just have extra paper here. I just wanted to point out. Yeah, I guess that's the end of it. I got 3 minutes. I'm going to use them. So a couple things. If you're asked to find something like, let's say, secant of pi over 3, we're going to find first. What do we do first? What's the reciprocal of secant? It is cosine. One way of remembering which ones are reciprocals of each other is, well, clearly tangent and cotangent have to go together. So just as a quick aside here, reciprocals. Clearly cotangent and tangent. They go together. They have the same name. That's also why it's good to say them out all the way, because then it's really clear. Oh, tangent and cotangent go together. And then we have sine and something and cosine and something. And here's the way I've always remembered it for some weird reason. Each pair of reciprocals has one regular function and one co-function. Regular is not a good name. I don't have a better name for it. I have tangent and cotangent. Here's sine, here's cosine. If they don't go together, they're not reciprocals. They're co-function. So sine has to go with either secant or cosecant. It's going to go with cosecant because you have to have one non-co-function and one co-function. Cosine goes with secant. I've written them in totally the weird order, right? Usually write them as sine, cosine, tangent, and then the reciprocals, cosecant, secant, cotangent. That is the usual normal. I know it's such a bad way to say it, but that's the usual way people write it. There are lots of good reasons for it, especially when you start learning about their derivatives in Calc 1. So if I want to find cosine of pi over 3, I'm going to draw this triangle. 30, 60, 90. Ooh, which of those angles is pi over 3? 60. And then let's see, in my triangle, the hypotenuse is 2, the short side is 1, and the medium side is √3. So then cosine of pi over 3 is adjacent over hypotenuse, so that's going to be 1/2. So secant of pi over 3 is going to be 2. Make sure when you're writing sine, and I know I didn't do it over here, it's kind of a sin. Not really. It's a math sin, not really. Make sure that when you're writing cosine or secant or whatever your trig function is, that there is an angle in there. And so writing like cosine, I can't even do it. I'm trying to do it. Writing cosine equal to 1/2. Oh, it feels so terrible. I hate what I've just done. It's kind of like writing the square root equals 4. Right? Like square root of what? There has to be a thing in your function you were doing the function to. So make sure whenever you're writing a trigonometric function, because they are functions, there's an angle or some theta or something you're taking cosine or sine of. So really here I should have written cotangent of theta, tangent of theta, sine of theta, just to not feel like it's the worst thing ever. Because there should always be an angle you are taking your trig function of. Okay, I've spoken enough. We'll talk more about this on Wednesday. I'll be over in C class. Looking for me. Okay, make sure I got these things in order here because it's kind of all over the place. Oh, no cap on you. That's not good. What's up? It's due on Sunday. So let's see, today's the 14th. So yeah, the 20th. Right, because it's copied from last year. So I'll update that. Don't worry about it yet. Correct. Correct. Yes. It'll be just like midterm 1 as far as the timeline. I will do my best to get I posted homework solutions today. I will do my best to get your homeworks graded before then. That's the goal. Maggie's like, don't worry about it.